In the zinc copper cell, there's a competition between the zinc and the copper for electrons, but Cu2 plus is more easily reduced than Zn2 plus. That is to say, in terms of oxidizing agents, Cu2 plus is stronger than zinc 2 plus. So copper is more easily reduced. Now, it would be desirable to separate the individual contributions to the total cell potential of the two electrode half reactions. However, it's not possible to determine the potential of a single electrode because for every oxidation, we have to have reduction. So therefore, it's necessary to establish some arbitrary standard to which we can compare everything to. And that arbitrary standard is the standard hydrogen electrode, SHE. Now, it's not really necessary to know much about the standard hydrogen electrode, other than to say the standard reduction potential is defined as 0. So if the SHE is used as an anode, here's my half reaction. And the standard reduction potential, E with the superscript, is defined as 0.000 volts. This is used as the anode. If the SHE is used as the cathode, we're going to flip this equation around. But again, the standard reduction potential, E with the superscript, is 0 volts. So this is the standard to which we can compare other half reactions to. So let's look at the copper SHE cell. The copper electrode gains weight, gaseous hydrogen is used up, the initial cell potential is 0.337 volts. At the anode, H2 goes to form 2H+. And the standard reduction potential, since this is the arbitrary standard that we use, is 0. At the cathode, Cu2+ goes to form Cu, and the standard reduction potential is 0.337 volts. So for the overall reaction, E cell, when I add the anode to the cathode, 0.337 volts. So by comparing to the standard SHE electrode, I can get the standard reduction potential for this half reaction right here with copper. So now that I know copper is 0.337, we can look at the zinc copper cell, and as noted earlier, copper plates out on one electrode. The zinc electrode decreases in weight. At the anode, zinc goes to Zn2+. Standard reduction potential is 0.763 volts. And at the cathode, Cu2+ goes to form Cu, and the standard reduction potential is 0.337 volts. So overall, standard reduction potential for the cell, when I add the anode to the cathode, positive 1.1 volts. So by measuring the potentials of several other standard electrodes versus the SHE, we can get a series of standard electrode potentials. And the resulting series is called the electromotive series. Metals at the top of the series are the most active. They have the greatest tendency to be oxidized. The nonmetals at the bottom have the greatest tendency to be reduced. So the electromotive series, here's a portion of it. And again, the metals at the top are most active. They have the greatest tendency to be oxidized. And the electromotive series will be given to you when you take the AP test. It's possible to get half cells for more complex half reactions. For example, 1 molar concentrations of Fe3 plus and Fe2 plus. The half reaction would look like this. And the standard reduction potential for this half reaction, 0.771 volts. Or 1 molar concentrations of Cr2O7, Cr3 plus, and H plus. Half reaction would look like this. And the standard reduction potential, 1.33 volts. But these more complex half reactions will be included in the electromotive series. The species at the top of the table on the right side undergo oxidation easily and are good reducing agents. The species at the bottom of the table on the left side undergo reduction easily and are good oxidizing agents. Now, any species on the left side will react spontaneously with a substance that's found on the right side of the half reaction located above it. So how do I know if a substance is going to react spontaneously? Right here. Compare the half reactions in the electromotive series. So here's another portion of the electromotive series. This includes the more complex half reactions. But again, you'll be given the full table when you take the AP test.